Alright, welcome back to part 2 of our online calculus lesson. This is the second lesson. This is covering section 8.9, improper integrals. The first video covered the procedure for doing integrals when one of your bounds was not a part of your domain. And now we're going to push that idea just a little bit further in this video. We're going to look at what happens in things like this. I want the integral of 1 over x cubed from, let's say, 1 to infinity. Now I know what you're all thinking. Dave, that doesn't make sense. Infinity is not a number. You can't plug infinity into a function. What are you thinking? I know! It definitely doesn't make sense. That's why this is an improper integral. We're not going to plug infinity into a function because it's not a number. We're going to make up a placeholder. Again, I always use b for things that are on top. I'm also going to change this around a little bit. And then instead of plugging in infinity, I'm going to plug in b and then take the limit as b goes to infinity. Pretty clever, right? All of your preconceived notions about things that you can and cannot do with infinity, I can circumvent all of them with limits. Limits are like cheating. They're great. So, I have solved the improper integral problem by replacing it with a placeholder and then taking a limit. I'm going to ignore the limit for most of this entire problem. I'm going to do this integral. I'm going to plug in the bounds, and then I will take the limit to see whether or not this converges or diverges. So let's see what that looks like. First I need to integrate x to the negative 3. And I'm pretty sure, I'll come back around here for that. I'm pretty sure that's going to look like limit as b approaches infinity of x to the negative 2 divided by negative 2 from 1 to b. So I'm going to plug in my b, get the limit as b approaches infinity of this negative 2. I'm going to pull that out and call that a negative 1/2 b to the negative 2 minus negative 1/2 1 to the negative 2. Now here's where things are going to get a little tricky. There's going to be a lot of, when you do the homework for this section, there's going to be a lot of b's and a's being raised to various exponents as you take the limit of those numbers as they go to 0 or infinity. And you have to have a really solid grasp of what these limits are going to look like as you play with them. So for this one, I'm going to bring it back over here. If you're not comfortable with the idea of having a negative 2 on this exponent here, if you're not sure what that's going to look like, make the exponent positive. This thing started in the denominator. We wrote it as a negative exponent so that the power rule would be very straightforward. If it being a negative exponent is hindering your ability to process what this is going to look like, put it back in the denominator. Negative 1 over 2b squared. That's what this b to the negative 2 is going to look like if you drop it into the denominator. B to the negative 2 is b squared down here. Negative 1/2 hangs out. That's just a coefficient. This is going to, double negatives will cancel. 1 to whatever is just going to be 1. So this is going to be a plus 1/2 on the back end, and I forgot my limit. Okay. So now I have the limit as b goes to infinity of negative 1 over 2b squared plus 1/2. And now I need to think about what this term is going to do, what it's going to look like as b increases towards infinity. When b gets really, really big, like a couple million, b squared is going to be a few trillion. And then if you take 1 and divide it by a few trillion, you're going to get nothing. So this piece goes to 0 in the limit, and the integral converges to 1/2, which you may not have expected from a region of the xy plane that is infinitely long. The area of this infinitely long region is about 1/2. It's not even a whole number. If we have to put a 2 or a 3 in front of this integral to get a number larger than 1 out of this infinitely long area that we have, this infinitely long region that we have just found the area of. So this is what improper integrals look like when there are infinities involved. I'm going to see if I can do an integral that converges to a number despite being infinitely long in both directions. So, what we've done so far is the basics of this section. I'm going to do one more example that is going to try to push the limits of what is reasonable. So if this next one is a little rough, don't worry about it. Focus more on the first three. That's the real meat of the section. This is just me being eccentric. I want the integral of x e to the negative x squared dx from negative infinity to infinity. I think that I'm going to get a number out of this. I think this integral converges, which I'm excited to find out because I'm trying to imagine something that would converge despite being infinitely long in both directions. And I think it's going to be this. I think it has to be e to some sort of negative exponent, or e to an exponent that is always negative. So if we take an x and square it, we get a positive number. You make that negative. You always have something negative. E to that negative power is going to always be, I think it's going to asymptote towards 0 in both directions. Let's find out. First order of business, this integral is improper. Negative infinity is not an acceptable bound. Infinity is not an acceptable bound. We need to switch out both of these. So I'm going to call this the limit as a goes to negative infinity, and the limit as b goes to positive infinity of the integral from a to b of x e to the negative x squared dx. So this is me doing my silly notational tricks to make sure that the bounds are acceptable. Now we actually have to integrate this. I think this one integrates as a integration by substitution. So I'm going to look at the inside. I think is going to be a negative x squared. The outside should be e to the blob, and the other will be a x dx. So I will set w equal to negative x squared, which means that dw is negative 2x dx. It mostly matches, but I'm going to need to put a negative 2 here. So if I put a negative 2 in front, then I need to put a negative 1/2 on the outside to balance that. And now I'm left with, if I can start here, the limit as b approaches infinity, of the limit as a approaches negative infinity of negative 1/2 still on the outside. The integral is now e to the w dw. Oh, from a to b. if I do that right. I'm not gonna lie, doing problems by myself in front of a camera is a lot more stressful because I don't have an entire classroom full of brilliant people to tell me when I've made a mistake. I found out this morning one of my other videos has a big mistake in it, and now it's just on YouTube forever. That was a little frustrating. I think this is okay. If it's not, I'll deal with it later. The integral of e to the w is e to the w. I'm going to continue writing these limits. The limit as a goes to negative infinity of the limit as b goes to negative infinity. I feel like I'm changing the order of these every time. If I'm doing so, it is unintentional and only because this order doesn't matter at all. Negative 1/2 stays around. The integral of e to the w is e to the w, and I'm evaluating from a to b. I need to unsubstitute. Negative 1/2. I forgot to write my limits. I need a bigger board if I'm going to write this many limits. The limit as a approaches negative infinity, the limit as b approaches positive infinity of negative 1/2 times w was negative x squared. So I'll have e to the negative x. I'm going to put in the a's and b's as well for space. E to the negative b squared minus, should be plus 1/2, e to the negative a squared. That just barely fits. Is it in the frame? Looks like it. I'll take it. So, in the no space I have left, let's talk about what this is going to do. B is going to infinity. As b goes to infinity, b squared will also go to infinity, substantially larger infinity. And then we make it negative. So the exponent on e here is negative infinity. E to something as a function looks like this. So if we're thinking about what happens to e to something as the exponent goes to negative infinity, we're back here. This piece is going to go to 0. This piece, the exact same thing is going to happen. As a goes to negative infinity, we're going to square it. We're going to get infinity. We make that negative, and now we have negative infinity as an exponent on e. So this piece is also going to 0. I was not expecting this to converge to 0. But now I see why it does. So let me write somewhere over here that this integral converges to 0. Now I'll explain why I'm surprised by that outcome. When I was trying to create this function, I was imagining the function e to the negative x squared. E to the negative x squared kind of looks like this, sort of like a bell curve-ish shape. The biggest point it ever gets to is 0, or when x is 0, the tallest point it gets to is 1 here. As x increases, negative x squared will get big, and the e to the negative exponent is just going to 0 out in both directions. This is the function I was trying to integrate. I knew that it wouldn't be integrable without an x here by substitution, so I needed that x there. So the function I actually ended up integrating looks very similar, except that x means that it changes sign. this is y equals x e to the negative x squared. Instead of being 1 when x is 0, it's going to be 0 because of this coefficient, not coefficient, whatever that is, product. And then it'll be negative on the back end, positive on the right end, in a way that is symmetrical, and that is why we get an integral that converges to 0. And that's what happens when I try to make up problems while filming myself. You can tell this is take 1, because I don't know what's going on. Still going to upload it to YouTube. This is all I have to say about improper integrals. I hope that you've enjoyed. I hope that this made some sense. Again, if this last one is unclear in some ways, I wouldn't stress about it. This is several orders of magnitude more difficult than anything that you should expect to see on a test or a quiz or the homework. The main goal of this is to replace bounds that don't make sense with placeholders and then take the limits so you can determine whether or not your integrals converge or diverge on that interval.